Okay, and we'll start the morning session with Surya, who will tell us about IVC for NP from standard assumptions.
Hi, everyone. I'm Surya. Today I'll be talking about IVC for NP from standard assumptions. And this is based on joint work with Pratish, Abhishek, Chanjong, Alexis, and Amit. And I will say immediately that I'm including IO in this list of standard assumptions. If you have a problem with it, you can take it up with some people, some of my co-authors. Okay, so what is IVC? I thought it would be nice to start with Valiant's original motivating example here. So suppose you have some very long computation that you would like to do. Maybe it's non-deterministic. I don't know, maybe you prove Fermat's little theorem, and then you keep making progress, keep computing, and eventually you have a proof, let's say, of a Riemann hypothesis or something. How do I trust that all these intermediate theorems that how do I trust that all these intermediate computations were actually correct without having to go over, a whole t time computation from scratch? So this was the original motivation. So IVC for NP, basically it takes the way to look at it is there's a configuration, ith configuration. There's a machine M with maybe a non-deterministic input that takes it to a new configuration, CF I plus 1, and so on. And the idea is that I want to set up a common reference string and allow allow a prover to run M while also proving that the computation so far is correct. So for example, at the ith step, you take in pi I as input, and then you output pi I plus 1, pi I plus 2, and so on. And the hope is that both the proof size and verification time is completely independent of the length of the computation so far. So I'll use capital T to denote hops. I don't have it on the slide, but if you see T, that's what it means. And soundness, I'll just say vaguely, is hard to come up with proofs for which CF0 doesn't go to CFT. There's no non-deterministic path that goes from CF0 to CFT. This will be adaptive soundness. And in this...
Is it obvious that you need a common reference string?
I think for the same reason you need it for snargs, you do. I guess if it's just one hop, you might not need it because you can just send the witness. But for multiple hops, there is some compression happening. So because we don't, I think you can have a non-uniform prover that could find a cheating proof.
But with uniform provers, you're potentially not needed. So we have work on this.
Oh, I see. It was really cool.
Uniform provers?
Yeah, uniform provers without a for snarks, not for us.
I see. That's really cool. Yeah. Okay, so just in case the distinction between snarg and IVC wasn't clear, so in snargs, you have a single guy who gets all of the configurations and in one shot gets one proof pi. Whereas in IVC, you can think of it as many people handing off computations to each other. So the first guy computes the first proof, and then this proof is now out of the picture. The next guy gets only this person's state, and then it keeps going. So really, you're not keeping around all of the configurations. You're throwing out everything you've done so far, and you keep going. Yeah? Any questions? Yeah?
This means that if you want to reuse something you have proved in the past, you cannot.
Why not? Oh, I see. I'm saying that this person doesn't need to look at it. It doesn't mean you can't publish this, for example. You could put this somewhere online. If someone wants to go from this state to some other state, you could go look at his proof and go from there, for example. Yeah?
You said that this guy gets the previous guy's state. By state, do you just
mean I just mean configuration and pi. Sorry. Yeah. Great questions. Okay, so application. So I never get to do the slide, so I kind of went ham with it. So one application is, for example, if you want to authenticate image edits. So for example, you take this one really cute picture of this dog. His name is Bean. And maybe you want to allow some kind of particular type of image edits. So for example, you want to allow someone to take this picture and flip it, or crop it, or color it, and so on. What you don't want them to do is do some terrible Photoshop of this picture, right? So what we can do is you can have IVC to authenticate each edit. So for example, this guy can authenticate that all he did was flip a picture, crop a picture, color a picture, and so on. And this is especially useful when you're trying to prevent misinformation. So for example, you might want to use this if you're trying to use a picture to say something in the news, for example. Another example that I want to bring up is verifiable shuffling. This will come up again later, so this is a slightly biased example. So in verifiable shuffling, imagine you have n parties who are voting, and you can imagine they encrypt the vote under a re-randomizable encryption scheme. And what you want to do is you want to shuffle this, right? Because I want to maintain anonymity. I want to shuffle all of these votes. OK, I have the wrong number there again. So what you can imagine doing is you have multiple authorities in the middle who take this list of votes, shuffle and re-randomize it, and you keep going. And as long as one of these parties was honest, you can hope that the shuffle remains secret. But the issue here is that maybe one of these intermediate servers decides to maul the ciphertext. So you could completely screw over the voting. So how do you prevent this? You can imagine you can attach a ZK IVC proof to each of these hops to ensure that all the work was done correctly. And now this server doesn't have to do L work when he's doing his shuffle. OK, and here I just want to, again, emphasize this is really IVC for NP, because the NP witness here is sort of like the re-randomization randomness and the shuffle, the permutation. So OK, how do we construct IVC? We've actually seen a lot about this in the first day of the talk, of the workshop. I'll say it again. So Valiant's recipe, roughly speaking, it says suppose you have two certified hops. You have CF goes to CF prime goes to CF double prime. The idea is you want to just take these two proofs and merge it. You want to merge it now to get a new proof that goes from CF to CF double prime, proving that you can do this in T plus T prime steps with a new proof. And hopefully you can say, well, this new proof has a knowledge soundness. So if you have an accepting proof here, you can extract accepting underlying proofs for the previous hop. And the crucial thing here is you want this new proof to be very short. You don't want to end up doubling the proof every time. You want this one proof to be the size of one of the underlying proofs, not both proofs. So to see that this implies having a merge algorithm like this is enough to get IVC, here's a picture of how you might do it. I'll try to go very slowly. So to go from CF0 to CF1, you'll first create some the base case proof. Then you'll create a second proof, CF1 to CF2. But now that you have two proofs at level 0, I'm going to merge them using this Valiant merging technique and forget this. So now I only have this guy sitting around. Now when I do the third computation, I'll do CF2 to CF3, CF3 to CF4, and then again I'll merge. But now I have two level 1 proofs. And so I can merge again. So the idea being, I want to keep this invariant, that I only keep around one proof per level. So I keep doing this. I'll animate it a bit more. Yeah?
By one you mean two.
Where?
By one proof per level you mean two proofs per level.
No, after you merge, you only have one.
Yeah, after you.
After you merge, yeah. You want to maintain that after you finish proving, you only have one proof per level. Yeah?
Why is this better than just sequentially?
You could sequentially do it. I think it'll become clearer in the IVC from standard assumption case. Here, I think it helps with making the extractor runtime better.
Well, what do you mean by sequential?
Instead of doing merging, I could merge CF0, CF1, and then have a proof here, merge, do it linearly on a path instead of a tree.
If you do it linearly, then you have a lot of space, no? But
No. Instead of doing it in a tree, I could merge CF0, CF1. I have a proof.
you merge this with that.
And then merge this.
Okay,
And
so
actually,
you
one
have
of our
multiple
constructions will look like that. But for this construction, I'm intentionally saying it this way because that will make more sense when we go to the standard assumption construction.
I mean, they're both true. One is balanced, one is not.
Yeah. But the recursion is different. But the recursion depth is different.
But the operation can be used for anything.
Yes.
It's only the...
But right now, as I said it, there's no difference.
Can you go back to the extraction thing? What did you say you need to do?
Sorry?
Can you go over say again what is that you need to extract? No, in the previous slide. The other one.
The extraction.
Oh,
The extraction?
I'm assuming you can extract the underlying configurations and the proofs.
I mean, there is some compression. So where do you get the extra information?
No, I'm saying this is the idea. This is from not standard assumptions. And I'll get to this. Okay. I need the last. Okay, so again, the idea is that at any point, if I'm here, I will only have one proof per level. So if I'm doing T hops, I'll only have log T levels. So I have one proof per layer, so the proof doesn't grow. Yeah?
So, can I think of this as some sort of a barg that I'm just
We will do that. But right now, think of it as a snark. Yeah, we will think of it as snarking the snark. So right now I'm doing background. This is like the original template. So Valiant's recipe is to snark the snark. So that's a level, you can imagine you have 2 level K proofs. The idea is now you just use a snark to prove that you have 2 underlying proofs for for this relation that says that I have the CF prime and I have 2 proofs, pi and pi prime, that are accepted by the previous verifier. So I can just like kind of recursively snark the snark. And how would you prove soundness? Like you would just say, okay, I have this cheating proof. I'm going to recursively extract. And at the end of the day, I'll get back this, the list of all configurations. So I know CF0 doesn't go to CF8, so you'll get a contradiction. And this is, again, an oversimplified proof. I'm missing many, many details, but I'm just giving this intuitive sketch of the vision from the original paper. OK. And there are many works that are, like basically take this and try to like actually write down like a nice security proof and do it from different assumptions. And we saw many of this from Benedict's talk. But in this work, I really care about constructing this from standard assumptions plus I/O.
What was the previous works? What assumptions?
So they use snarks. There's arithmetized ROM model, which is not ROM, but like arithmetized, like a different ROM accumulation schemes. Yeah, there was a talk on this on the first day. But this talk, I really want to think about IVC for NP from standard assumptions. And I want to say here again, like I'll get to this soon, IVC for P from standard assumptions exists, and we really piggyback off of this result. But the first problem is snarks do not exist from standard assumptions. And I don't quite know how to do this proof without going through extraction. So it seems like some kind of knowledge soundness is really important. And again, we saw yesterday that bargs tend to replace snarks in this, and this is exactly what we're going to do. But before that, I want to ask, what about the random oracle model? Snarks exist in the random oracle model. So can we do IVC in the random oracle model? And in fact, Valiant's original construction, first it uses random oracle as an oracle, and then a concrete function, and then an oracle again. So like here, when I'm like writing this relation down, I'm treating this O as a concrete function, whereas here I'm using O as a random oracle.
What do you mean by that?
What do I mean by that?
What's the difference between a concrete function and a random oracle?
Random oracle is like a big random function in the sky.
Okay.
And it doesn't have a small description. Here I'm pretending it has a small description.
Because you're proving a non-black box. You're saying you're proving something about the verifier with O. So you're actually proving something about the
I
circuit.
see your statement involves.
The statement involves this O. Yeah, you've doubled the chip. This is not good. And I like this phrase that Benedict used, which is security gap. There is a security gap here because you're like going between like multiple different models about the ROM. Yeah, not great.
There's already a security gap between the ROM and the real world, so it doesn't
That's
matter.
fair.
So okay, so we're already in gap land.
Yeah, but if you use random oracle all the way and solve it, and then you PH me or something, I'll be happier.
Okay.
And in fact, this type you can construct snarks in the ROM for these kind of like languages with like oracle access. This is shown in this work by BCG. And there's also a different work that showed, that there are really some barriers to IVC in the ROM. This is a bit complicated to state, so I didn't put it here, but you can look at the paper. So, it says in the ROM, like it feels like snarks and IVC are very different problems. Okay, so here's the game plan for today. First, I'm going to say it up front, I'm going to give up on knowledge soundness. I'm not going to hope for knowledge extraction of the whole path from my IVC because there's this work that basically says, you can't hope to construct snarks from black box via black box reductions that have knowledge soundness. So now, how do you prove soundness? We can't use snarks. So in this work, we give 2 different approaches. So one, So from standard assumptions. So the one is extraction based. And as Shafik asked, you can replace snarks in this instance with bargs. And the proof size we get here is poly in lambda and an intermediate configuration size in log t. And I want to say up front, this really relies on tools from prior works by Omer, Raphael, Lali, Rishab, Yael, and Vinod. So if you've seen this before, this proof will not be that surprising. But the second result, I was not satisfied with this dependence on CF. So we decided to think about it more, and we construct even more succinct IVC for what I'm going to call trapdoor NP languages.
What were you unhappy with the fact that you go with the configuration?
Yeah.
That's unhappiness?
Yeah.
Okay.
Yeah. I'm not happy with this because we can do snargs that are better than this. Why do I need to pay for this in IVC? And so in the second result, we try to get rid of the CF dependence. We do it for some subset of NP. I'll talk about this more later. And I won't show in this talk, but we achieve ZK in both settings. Yeah. So any questions? Yeah? Yeah?
So the succinct IVC is not for all of NP, it's for a subset of NP.
But yeah, I'll explain what that means in a bit.
Okay, so just so, for all of NP, we still don't have IVC from, like, IO.
From IO, yes.
Yeah,
And
you need to go
so
back to the
I want to think of this talk as giving you an open problem to work on.
Yeah.
Yeah.
And for that, you still need to go to the double gap thing with random oracle.
I mean, you have this.
No, this already achieves the
This is
efficiency
IVC.
in the-
Because
But if you want, not,
polylambda,
just, if you want that result, you're back to,
snark.
basically, yeah.
Yeah. And this is the dream. I will, hopefully by showing this, I can give some people intuition for where this trapdoor comes in.
Wait,
And, yeah?
does that approach really give you the right succinctness?
Which approach? Well, if you rely on random oracle, you can get whatever you want. If you got random oracle, but then it's not random oracle, and then it is random oracle, then you can get.
Actually,
It's not clear,
you know,
right?
could there be that there is a hash function that realizes random oracle things
Sure,
and
yeah,
not
yeah.
doesn't realize the iterated random oracle? Can it be that there is such a hash function?
Oh, that I don't know, but if you
I don't know
assume
either,
that.
but that's a good
If you
question.
BBB,
Hash of
I think if you use
I know.
BBB, actually, this will work also.
Yeah, exactly, yeah.
Yeah.
Makes sense. Okay, good.
Yeah?
So the first result is the IO used for this, not for NP, is that the?
Yes. Yes. And I'll say a corollary that doesn't use snarks for NP, that doesn't use IO. So there is actually one result here that is from, hopefully, LW is hopefully a standard assumption. Did you have a question? Yeah. Sorry. Any other questions? No? Okay. Okay. There's a trap. Anyway. Let's see. Okay, so the first result is that we construct IVC for NP, assuming sub-exponential hardness of non-adaptive snark for NP. Actually, maybe because I guess in the non-adaptive setting, you can use complexity leverage to make it adaptive because you're assuming sub-exponential. So that's why non-adaptive is sufficient here. And rate 1, some are extractable bargs.
I didn't catch that.
Yeah.
The result is still adaptive, IVC.
It is adaptive. I'm just saying that because we're using on sub-exponentially sound snargs anyway, you can get the efficiency to get this result by just complexity leveraging a non-adaptive snarg.
Okay, so you were anyways going to use complexity leveraging for other reasons.
Other reasons,
and by
yes.
the time you use them, might as well use them
Yes,
for
exactly. Yeah. So I'm just stating it this way because I just wanted to make sure that, we didn't, it says that I don't need, like, waters woo, Sci-Fi waters is enough. So, like, you need, like, the slightly less complicated, like, instantiation of it. And, yeah, I really want to emphasize here, this is incremental, very thematic. And you can think of this as a careful complexity leveraging of these prior works that I mentioned before, which show that assuming rate 1 some are extractable bargs, there exists IVC for deterministic computations. Okay. And again, I want to emphasize this is independent of the number of time steps, so this is already very interesting, but it does grow with the intermediate configuration size, CF. Okay, so I'll get into the construction. So the protagonist for this part,
Another question?
yeah?
And the reason why you can't show off memory on the side is because from standard assumptions, we only know how to do memory delegation with like a known...
Exactly.
Something like that, something like that. Yeah, I don't think it's inherent. Like, I want to say that because I want to say, I'll show the second construction, it doesn't do extraction. There it doesn't seem very inherent, except I don't know how to do all of NP without using a hash function. So that's where it comes in, but for the first result, yeah, it's because of the extraction. It's extraction
But
piece.
so the first result could also be a viable stepping stone. Like you could potentially get rid of the configuration size maybe there. Like,
I don't think so. This one feels more, I'll show the picture, and I don't know how to get rid of it.
Sorry, what was the question?
Can you get rid of the configuration dependence in the first result? Yeah. So we saw bargs yesterday, and today we'll see slightly more efficient bargs. So to recap, a barg is a snark for this special type of statement where you get a batch instance x1 through xk. And the prover has w1 through wk for each of these witnesses. And the goal here is I want to send a proof pi that proves all of them that only grows roughly with one of these witnesses. So I think someone asked about this during Omer's talk yesterday. Yeah, wi is like information theoretically what you sort of need for somewhere soundness or somewhere extraction. And okay, the reference will show up soon. But yeah, we do know how to get this. And yeah, to compare with the usual barg requirement, in usual bargs we only require that the pi doesn't grow with k times wi. It just needs to be much, much less than that. And again, just to recap the soundness property we require from bargs, or somewhere extractable bargs, it's this property that you can generate the CRS in a trapdoor mode that can guarantee somewhere soundness. So you can generate the CRS in this mode I star, which lets you, if you have the trapdoor, you can extract a witness for the I start statement. And again, we want this property that, even if it's in trapdoor mode, you can tell that it's in trapdoor mode.
You're okay if the CRS depends on k, right? The length of the CRS depends on linear and k or even quadratic?
It's fine, but I think we know how to generically...
It doesn't need to.
Yeah, it doesn't need to, because you can kind of recurse.
Yep. Yes.
Yeah. So yeah, I think this is a paper by Yael, Alex, Vinod, and Daniel that shows that you can generically make it short. Okay. And for the construction, see how these works. I wish I could go over this, but intuitively you kind of break the computations up into smaller pieces, and that helps you get all the way to rate 1. Okay? So again, looking back at Valiant's recipe, as Shafik already said, we can try to rely instead of somewhere knowledge, soundness. So yeah, I stole this phrase from Lolly, barg the barg. So instead of snark the snark, we barg the barg. And that's the nice thing about rate 1 because it lets you barg the barg without blowing up the parameters. So now basically instead of merging with the snark, I'm going to merge with a barg, which basically proves it's going to have 2 statements, k equal 2. So CF goes to CF prime, CF prime goes to CF double prime. So this is a statement. So basically those 2 configurations become the statement. And the barg witness is going to be the 2 underlying barg proofs. The level k plus 1 proof is a little subtle, but it's CF prime comma the barg proof. So you have to keep around the CF prime because you can only verify this proof if you have this full statement. And this full statement requires you to know the midpoint. So you keep around CF prime here. But this will end up being okay if you think about the recursion because each time I merge, I'm only going to pick up 1 factor of CF prime. So I only pay for roughly log t times CF. Yeah? Okay.
This is where the dependence came from.
Yes, exactly. Because I don't know how, I need to know CF prime somehow to be able to have soundness for this barg. So I'm just going to give it to you in the clear.
Can I ask you 1 second? So if you give h of CF prime, hash, now it's short.
Yeah.
Okay. Now for the first statement, you can easily verify given hash, it's still p.
Yeah.
Let's say I have to.
Yeah.
For the second statement, you can use ram snark because you know
Yes.
configuration.
Yes.
So why
this
can't
isn't
you-
P. You're saying this for P.
Okay, sorry, you're still in the p land.
No, what you're saying might work for P. Is what I'm for
Yeah, it's the
deterministic
configuration
because you can
for-
actually compute given CF, you know what these 2 should be. You can actually compute it. So it's as if you can do a RAM delegation because it's as if you have all the configurations in your hand.
I guess what I'm saying is if configuration prime is unique, I don't care how you got from configuration prime, maybe with a witness.
Yeah.
But if configuration prime is unique,
Yes.
then you can shrink it and use RAM.
Yes, I 100% agree. But again, I want to allow for computations where you can have many
Where you're
different.
saying configuration prime may not be unique.
Yeah,
That's your
for example, verifiable shuffling, it could be many different things.
Okay, got it.
Yeah, but you're completely right. I think at least IVC for P, you can get rid of this configuration dependence. I think
Yeah.
if you
Yeah,
stare
yeah,
at
yeah,
this,
So you're saying something for P, but support large configurations in the middle, not in the end, maybe? But
All
Yeah.
I'm saying is if you do even NP, from configuration to configuration prime was an NP state computation, but where configuration prime is unique, then you can also show. Yeah, there's a many
No,
places.
unique ith step is enough, I
But
think.
let's say I give you a hash of a configuration, it's not the right configuration, it's not CF prime.
Then you'll
How can
fail
you
the
verify
first.
the second part? Could be
You're
that.
gonna, we'll pick it offline.
Yeah. Okay. Yes, but you're right. What you're saying, I think you can get rid of this dependence for P. So what's the construction? the base case is just going to be a snark for NP. This is where we use snark for NP. The reason I want to do this is because I want to get rid of this dependence on W. So there's secretly a W here. So I'm instead going to use a snark to prove that there exists a W that goes from CF0 to CF1. So you can imagine if you just use a trivial snark, you can also get something here, but base case is snark for NP. Then you barg, same thing as before. Yeah? So it's exactly the same construction as said before. Yes?
Sorry.
Yeah.
Do you know that you need the configuration, like to grow with the configuration size only inside the proof, or that you simply need it to compute the next proof? Because there's like also an option.
Yes, but here, if you remember here, I only need CF double prime to compute the next proof, right? But I need to keep around the midpoint of this computation inside the proof for the verification. So I'm not thinking, when I say proof size, I'm not counting the first configuration, the last configuration, but somehow I still need to keep around this midpoint.
Thank you.
Okay. Merge variate one barg. Okay. So just to give a taste for what the proof strategy is, it's very similar to what Omer presented yesterday. So okay, I'm leaving this here just in case you need to look at it. But okay, suppose you have A that creates cheating proofs at this point with probability at least epsilon. Then the pigeonhole, there's one side that he cheats more on, right? There's one side, let's say the first one, that he cheats on with roughly probability epsilon over 2, just by pigeonhole. So now you just switch to CRS binding accordingly, and then you say by the index hiding probability property, he should still be cheating there with probability epsilon over 2. And then now you can extract and recurse. But I'm hiding a few details here because right now we're working with NP, not P. So remember yesterday Omer said, you can do this if, given the configurations, you can decide efficiently that you can go from CF to CF prime. But here you have an NP statement, but actually careful complexity leveraging is good enough. So if you set the parameters so that, this 2 to the configuration size hard, that's good enough to make this type of argument. Okay? And that's the only, I think this is the main difference between this and the works for P. So just to give a pictorial sketch of what's happening, you have a proof there, you extract, let's say you extract the left side, and you keep extracting. And the point is you're not extracting more than the size of this proof, right? Information theoretically, you have enough information to extract. So the point is you can recurse all the way and get all the way down to this point, where you get 2 adjacent configurations that do not have a witness. So at this point, you can extract the underlying snark proof and break snark security. Yeah?
You really use the fact that you're a tree, not going in.
Exactly. This is where I need the fact that it's a tree. Because I'm losing this factor of half. I think there might be ways to get around it. I think there might be, I think Omer has some ideas for this. But at least for now, if you use this type of simple CRS binding trick, I don't know how to do better than this.
But when you do it from bargs, if you want to do a chain, you'll lose in efficiency because we do have some growth.
Yeah.
I see.
Because the rate 1.
Yeah,
I see. Yes, that's also true. Yes. You're totally right because you have this additive factor. So that's 2 reasons.
About security.
Yeah.
So if you have short witnesses at each
Then you
step,
can just keep
you
not
can just
use the
do a
snark.
trivial snark at the base?
Yes, I'll say that on the next slide. Yes?
Yeah, how do you know which path to extract down?
So this is where you really need to use some complexity leveraging. So given this, you can sort of at this point you'll have CF0, CF4, and the midpoint. I can look at it and non-uniformly decide which side it's cheating more on. And then I can go, and then I set the CRS to extract on that side. Yeah, I'm really.
But you can guess, right? Let's say you guess.
You can guess. We can
Then
guess.
you can guess probably 1 over
But then, but you still need to argue that he doesn't cheat out. If you guess and then he doesn't cheat outside of it.
Yes.
For that, you need this kind of complexity leveraging.
But you need to use the hiding.
Yeah, you need to use the hiding, and arguing hiding is a bit tricky when it's NP, just a bit, not that bit, not that bad, but yeah, that's why I'm saying it this way. So if you do it carefully, non-uniformly decide, then you don't have this issue that you'll cheat elsewhere when you program the CRS. But there's a very big circuit that can decide this, but it's not too big. So you can set the security parameters correctly to make this go through. Yeah?
The other question I had
Sorry.
was that the statement Does it grow because you're writing like proofs about new statements at each layer?
Yes, but you're picking up like an additive poly lambda factor each time.
Okay.
Lambda will be like the size of one configuration, let's say. But that's still like log t times that you're picking it up. If you do the recursion, it will be like poly and configuration log t. Yeah?
You said for complexity leveraging, you need like security more than the size of the configuration.
Of the what?
Like you need the problem to be harder than 2 to the size of the configuration.
Yes.
So doesn't it create like doesn't it constrain you to choose a security parameter that's large enough?
Yeah, it does. It does. But that's why I'm saying there's a factor of the configuration size that shows up anyway. So it shows up for 2 reasons. One, because of the fact that I'm like actually keeping around a configuration. 2, it shows up in the lambda because my lambda needs to be big enough. Yeah. Yeah?
So in other words, even if you do IL strict and like hash the inner configuration, you still pay for it anyways.
Sort of, yeah. I guess, yeah.
No, inside the security parameter, not a grow with the configuration.
But then you can't.
But then you can't do this CRS hiding trick because you can't decide. We can take it offline, yeah. Yeah, it's a bit in like very low level detail, so we'll talk about it later. Okay, so to say it again, we have now IVC for NP from sub-exponential hardness of I/O and one-way functions, and either LWE, DLIN. I can't remember what other assumptions, but a lot of standard assumptions. But I want to say here that, as we already said a couple times before, if you use a trivial snark, it just means you pay for W at the base layer. You can actually get a proof size that grows with one witness, poly in one witness, one configuration, and log t. And now you actually get a corollary that doesn't use obfuscation.
What's the difference?
The difference is there is a trivial snark that I can use, which is send me the witness.
Oh, I see.
If you remember the picture, that's fine. I just pick up a W at the base layer.
Oh, you added W there.
You added a W there. And this is still meaningful because you can imagine like T is the biggest dominating factor in this computation. Maybe my witnesses are small. I'm paying for 1 versus W times T. That's a big difference. Okay. Okay. Perfect. Okay, so this is where I'm a little bit unsatisfied because we know how to do, this feels like a related problem, adaptively sound snarks, because, like IVC is also adaptive. And here in this adaptively sound snark regime, it seems like we can get polylambda proofs. Even though we use complexity leveraging and all these things, we still can get polylambda proofs. And I'm very sad that this talk wasn't this week. It was during the obfuscation week. But if you're curious, there's a recording of it. But I would like to plug this as a very cool result. And I'll try to tease out one of the ideas from this work in my security proof. So if you follow this proof merging template that I mentioned, it seems like we're really, really stuck at this configuration size dependence because you need to put CF prime in the proof and then recurse. And I don't want to do that because I want to get polylambda size proofs. So I want to do IVC without any extraction. Try to come up with a completely different way to do it. And if this really smells like I/O. If you've done I/O proofs, like I/O somehow, every time it looks like you need extraction, you get around it. So that's what we're going to try to do. So our result 2, even more succinctness. So there exists IVC for trapdoor computations M, assuming sub-exponential hardness of I/O and injective PRGs. And what's a trapdoor computation? It means that for this M, there exists an efficient trapdoor that lets me decide if a hop is valid. Without this trapdoor, I know nothing. With the trapdoor, it's basically I can immediately tell. So this might seem strange, but I'll show an example on the next slide. But for this, we get proof size polylambda and log t. And at this point, I want to say the trapdoor only appears in the proof. This is kind of like the universal snark talk from yesterday. It's quite inspired by it, actually. So the person who delegates does not need to know this trapdoor. So that's the thing that makes this useful in applications. So you can generate the CRS, but you can guarantee soundness even if you don't know this trapdoor. And you can guarantee adaptive soundness. Yeah?
Can I think of
this trapdoor is kind of like a universal witness for any statement? Is that?
No, it's like a secret key for, okay,
Because normally like a witness is kind of like what you need.
Yeah, I understand. Look, maybe this example will clear it up. So this is the verifiable shuffling example I mentioned earlier, which I cherry-picked because I can explain it here. Here, the trapdoor is really the secret key of this re-randomizable encryption scheme. So for example, using this trapdoor, I can decrypt the ciphertext here, decrypt the ciphertext here. The hop would have been valid as long as this is a permutation of this. So there's a very efficient trapdoor that I can use to determine if any hop is valid, but you don't need this trapdoor when you generate the CRS. So this actually gives the first like multi-hop verifiable shuffling scheme, the short proofs from standard assumptions. Like this was known before the generic group model and from SNARKs, and this gives a plain model construction for this problem. Yeah?
Why is this like a, like for example, like this doesn't actually, like what does this actually tell you? Because like what if like the first server could like just like let's say like arrange the ciphertext in an order that he determined, right? And that's
no, I'm saying it tells you that you can't, the goal here was to make sure he doesn't maul the ciphertext. So okay, yes. So the point of verifiable shuffling is as long as one server is honest, the shuffle is a true shuffle.
Okay.
The point of IVC here is to help you make sure that nobody tampers with the underlying messages.
Okay, so it suggests that like...
It just means that, fine, if he just does the identity function, that's fine. Or does a very silly shuffle, that's fine. But the point is he cannot change what's underneath the hood of the ciphertext.
Okay.
Right? Like because it's a voting scheme, I want to make sure he doesn't change what the votes are.
Yes, for randomness, it's sufficient that one of them is good.
Yeah.
But for not changing the vote, you need to check that each one.
Each one is good. So here, does that make sense? Yeah, sorry, this is
I'm just curious what the, I guess the definition of this trapdoor. Like.
Yeah, the trapdoor here is, okay, the IVC guarantee that I want is to say that these are true re-randomized shuffles. Each step is a randomized shuffle. Don't forget about like the voting security and whatever. The only soundness guarantee I need is that the servers do not change the underlying ciphertext. So for that soundness guarantee, this is the trapdoor.
Okay. For the fact that it's a shuffle.
Yeah.
Get randomized.
Yeah.
The fact that it's actually a shuffle.
Yes, exactly. The re-randomization is just there for the zero knowledge for the underlying scheme. But the way, this is how people usually implement this thing. And I'm saying, like, each step can actually has this property that you can verify it.
So in general, trapdoor computation, will you have a definition or no?
Yeah, here.
Okay, so tell me what, this is a definition? No, this is a theorem. What's the definition of trapdoor computation?
Exactly. I should have written it better. So this is the definition of a trapdoor computation. So M is a trapdoor computation if there exists a trapdoor, TD, that lets you efficiently decide if xi goes to xj.
I see.
And this sort of makes sense because here, this is a language where you don't need the intermediate configurations to decide. So it makes sense that this is what we can do, but I think we can do more. So,
I see. Trapdoor is just, you say if you could get rid of your intermediate computation by definition using some secret information.
Yeah, but at least in this example, it makes sense that you still want these intermediate configurations to exist, right? Because you want to shuffle. Yeah. So just a meaningful way to interpret this theorem is via this verifiable shuffling.
Sorry, minor thing. The trapdoor, as written, does not know the time of xi.
J minus I. Sorry.
No, it knows just the gap.
Yeah, it's just the gap.
That's important, or like could it be that you give I and j as separate inputs?
I see. I think maybe you should do I comma xi, j comma xj instead. Okay. I think it depends on the language. I think because I was thinking about this verifiable shuffling.
Depends on your proof.
Yeah. Okay, think about it as numbered.
Okay.
Why is it relevant then?
I think you can always like change the language based on what you want, right? You can define this xi to be I comma xi.
I mean, their theorem probably holds for both definitions, right?
Sorry?
Your theorem probably holds for both definitions.
Yeah. I think it does because one subsumes the other.
Yeah. Thank you.
Yeah.
I still don't understand. Is this a definition? Is this a theorem?
It's a theorem, and this is a definition of trapdoor computation.
So the first line is a theorem, and after that is...
Yeah. Sorry, I should have written it slightly better.
One configuration.
So this is the definition of trapdoor computation.
Yes.
Yeah?
Sorry, can you say a bit more about this trapdoor itself? Like, what is it? Is it efficient computation?
It's an efficient circuit, deterministic, that can decide this.
And it, okay, and it like knows the language, like hard coded.
Yes, yes. So like M comma TD, you can think of it as like a pair that comes together.
So do you have other examples of trapdoor computations besides the shuffling, or is that the thing we should focus on?
There are, it's hard to come up with the ones with NP steps, but there are other examples I can think of where you can get poly-lambda size proofs. So for example, you can think of any search problem with exactly one witness. That witness is your trapdoor. And then you can think of xi comma xj as like a range that you're searching on. And you can certify the range doesn't have the witness, for example. So I think there are other interpretations of this. This is the one I decided to choose today because I think it really shows the NP.
Is there any possibility that every language in MP has such a trapdoor?
No, it should not, right? This is like
it seems
co-NP. This will put it in co-NP. This is really about keyed. You should really think about keyed languages for this. Like for example, like secret key, public key pairs, and so on. And yeah, this will immediately put it in co-NP.
Right.
Actually, not even worse, like co-P or something. Like you can determine in polynomial time if two configurations are reachable, like the no instances. Actually, it puts it in P. It puts it in P.
It puts what in P? So the subset that you proved
Yeah.
for is P.
Yeah. It's P, but again, I'm saying like you don't need to know the secret key.
Yeah, exactly.
Yeah.
Wait, I'm confused.
Yes,
I'm
yes,
confused. This is a theorem that there exists in IVC for a subset of NP. Is this subset of NP greater than P or not?
I think it's equal to. It's
because you have the secret.
Yeah.
It's a weird.
It's a keyed
key. If you know a secret, but you may not know a secret. Kind of
It seems difficult because if you have like a P-complete computation, something that requires a lot of sequential time, here the verification time is bounded, so it seems that...
like a time lock puzzle or something.
Yeah, exactly. It's like that. It's like a time log puzzle.
We didn't hear.
It's like a time log puzzle where there's a...
Like a time log puzzle.
You cannot do that.
Isn't it simply non-uniformity? Like if
Yes,
you need
yes.
one witness for, not for like one witness for one instant, like one witness for all.
Oh yes, I understand, yes. I want to get rid of this. I'm not saying this is the end of the line, right? I'm saying I want to get rid of this. But there are still... Yeah, but there are meaningful interpretations.
Yeah.
Okay, so this is highly inspired by like this pure I/O adaptive snark chaining approach of like these works by Waterspoon and Gentry, Devdas, Waterspoon, lots of Waterspoon. Okay, so since I can't believe I'm the first one this week to define I/O, but I am. So, ta-da! Okay.
Why did you get to I/O?
Because my theorem uses I/O.
I see.
So now I'm gonna prove the theorem. Yes, exactly. And I/O, it's this thing that says that if you have a thing, okay, sorry, I'll do it the right way. You have C1 and C2, and if they're functionally equivalent and I obfuscate them, I cannot tell obfuscations of C1 from C2. So the intuitive way to remember this is that you have you kind of can only see the truth table given the obfuscation of the thing. Okay, so now the construction. The idea is very simple. If I give you obfuscation, this is probably what you'll try to do. And in fact, Benedict actually had a really pretty picture that ends up being exactly what we do. Basically, you're going to have the snark prover be someone who takes in the configuration and a proof, verifies the proof, and outputs the next proof. So as long as you give me a good previous proof, I'm going to output the next proof. So basically, in words, what this is going to do is you're going to have a PK and VK algorithm, where K is like a PRF key. You're going to sign a message, a configuration x0, xi plus 1 if it's valid, and you have a valid previous proof. And verification is basically checking if you have a signature for that statement. And the CRS is going to be just the obfuscation of these two algorithms. So if I give you a VBB, this would be exactly what you do, and I think it would work. But if you don't have VBB, you have I/O. So it's completely unclear why this would be secure. So I've tried my best to try to show this. So the security proof I'm going to show in from macro scale to So I'm going to start with, in the real world, this is what the verifier looks like. The verifier looks like this guy that just looks at a proof pi and checks if it's a valid signature. And then after that, you do way too many hybrids. And the goal is I'm going to go to this ideal world where I'm going to remove all the proofs for incorrect statements. So I'm going to use this trapdoor under the hood of this verification to remove all the proofs that for x or xi that are not in the language. Yeah? So why is this so why is this good? Now a cheating prover gives you a distinguisher between these two worlds, right? You can calculate, given a cheating prover, you can calculate his success probability here. If it's more than 0, you've already broken indistinguishability. So this is really like, we're not doing extraction here, we're trying to argue it a very different way. We're trying to say we're going to remove the proofs. Okay? And once you have this, you have soundness. Okay. So now, how am I going to go from H real to H ideal? H1, I'm going to define as being the hybrid where I've removed all the proofs for 1-hop statements. And then 2-hop statements is going to be H2, and so on. So zooming in a little bit more, we're going to have like these intermediate checkpoints where I'm going to remove like one layer of proofs at a time. So again, so HK is going to be the hybrid where I've removed all proofs less than or equal k. Here I'm going to remove all proofs less than or equal k plus 1. And so the rest of this talk is going to be about this step, how to go from HK to HK plus 1. Okay, this is going to be the template. And this time, now at this scale, I have exponentially many hybrids. Yeah?
Sorry, could you define again, like, what do I get in HK? Like what?
Yeah, HK, you can think of, I'm just hiding the prover algorithm because the prover eats this verifier. Right. So this verifier algorithm that I'm going to obfuscate is going to already internally reject every single proof for I less than or equal k. Because in this verifier, I'm going to put the trapdoor inside of him. So this trapdoor is only going to appear in the proofs. I'm going to put the trapdoor inside, and he's going to automatically just have the trapdoor inside and check if it's a valid hop, and automatically reject.
Even if it is valid?
If it's not valid,
oh,
TD
okay,
equals
okay.
0. That's yeah. Yeah.
You mentioned this like analogy to like adaptively starred sound idea. Like, is
No,
that
this
somewhere
is
here or?
no, it's not here.
Okay.
It's in this.
Okay.
In this magnifying glass.
Gotcha.
I'm trying to defer I/O gymnastics as far as possible by giving the macro level first. But this chaining idea is from I think Lolly Waters Wu does it, and I think what? The adaptive one, but the Ratchet et al. Did it for the non-adaptive setting for bargs, and that's where the chaining idea comes from.
Can I ask you something?
Yeah.
Suppose I came into the talk right now, okay?
Yeah.
Without everything you've said so far, and I wanted to understand extraction versus this idea where you're saying that there's no proofs.
Yeah.
Okay. Could you what would you say? Start from this point.
Yeah.
Okay, of view that there is an extraction method for proving soundness, and you are proposing a new method for proving soundness, which removes proofs. Okay.
Yeah.
Can you explain in this language what's happening right here?
Yeah, here I'm saying that instead of trying to keep around information in pi that I will extract and check, I'm instead saying I'm just going to directly look at x0, xi and not look at this proof here and decide whether I want to reject this. And this is not extracting anything from pi.
She assumes you have magic information that helps
Yeah,
you check.
I am assuming this, and again, this is not where I wish I could get rid of this requirement, but at least with this requirement, I want to show what the proof looks like.
If you had this
trapdoor. And it makes sense, because with this trapdoor, I don't need to extract. It gives me a way to decide, it gives me a way to just look at x0, xi directly without knowing anything about the intermediate configurations. So that's the point I'm trying to get across. And this is at least in this regime, we should be able to do it, to get polylambda size proof. And we can. This is what this proof is going to show. But I want to. I'll show exactly where I really, really need this trapdoor. I will say, I guess for those of you familiar with Waters and Wu, I think these two steps are not the main reason, not the bottleneck for where I need the trapdoor. I'll have a slide on this to explain where I really, really need the trapdoor. Yeah.
This might be
Following also Alice's question,
Yeah.
FK is a MAC. Can I think of
Yes,
it as a MAC?
yes, it's a signature. It's a PRF signature.
But then in the security you need 0 and I, like, it will rely on unforgeability of this MAC probably.
Yes, 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 yes.
So if you put just the delta, how can you improve it secure?
The
Don't you need the
delta?
beginning and the end of the configuration?
Yeah,
to avoid
sorry, I forgot. I changed all the CFs to X. So these X0 and Xi are like configurations X0 to Xi. This verification algorithm is taking in the start and the end, right?
Oh, okay, it's from the start. Okay.
Yeah. It's taking in both. Yeah?
So the whole point is this trapdoor that makes it so short. If there was no trapdoor, then those lines would be just check all the other computations.
Yes,
and
yes,
just
exactly.
answer this.
There is a way to shortcut
Then
it.
it would be way too long.
Yes.
And so with the trapdoor, you can make it short.
And again, I wanted to give this talk in a straight line way without talking about, like water through why that didn't work at this step, yada, yada, yada. But this is not where it comes in, I think. Like, it's not because I need to efficiently decide the language inside the circuit. But I'll talk about it.
So there's nothing happening here except for this trapdoor.
Yes.
Yeah.
Yes. So this is where it shows up when I would do this induction. So I want to output the next, notice that this is what the programs look like at HK, where I've removed all the proofs until K. So notice that the cool thing here is that I will, K plus 1. If K plus 1, X0, XK plus 1 was wrong, the prover algorithm never reaches this line for that input. Because either XK doesn't go to XK plus 1, so that means I'll never go past this step, or the first hop is wrong. So that means I've already removed the signature for this hop. So if my input to this was not valid, I'll never invoke the MAC on this input. And this inductive step is where I really need this trapdoor. And this is where I can't get rid of it. So this is the open problem. I don't know how to do this inductive step. Because for I/O status, I really need that things are functionally equivalent. And even if I say something is hard to find, that's not good enough for me to do I/O security. So that's the high-level point.
So are you saying with VBB you wouldn't need the trapdoor?
Yes. VBB, this will be secure. Okay. So time for I/O gymnastics. And this is going to be based on a lot of techniques from a lot of amazing works on snarks and I/O. I've listed them here. I have I put some of the references at the top of each slide accordingly, but this is the full reference. Okay. So the first thing we're going to use is puncturable PRFs. I've tried very hard to defer this to as much as I can. But basically the idea is a puncturable PRF is a PRF which has this extra mode where you can take a key K and puncture it at a point X star. And the point is correctness is still maintained by this punctured key at every point other than X star. So the two FK star and FK are the same everywhere else. And the point is that for security, you get something interesting. You get the fact that K star actually doesn't tell you much about FK of X. So given just K star, you can tell FK of X from a truly random value. So K star really doesn't reveal the punctured point. And this ends up playing very nicely with I/O to let you do some crazy I/O hybrids. And I don't have much time, so I might do this pretty fast. If you're curious, come talk to me again after this talk. But OK, let's say for now I'm in H0, and I want to remove one hop. I'm going to remove one proof. So let one Z0, Z1 be an incorrect hop. Step 1, I'm going to puncture the key at this point. Because again, I'm never reaching this step here. So I can puncture the key. OK, so I'm going to puncture the key K at this point. And I'm going to add a hard-coded check of pi equal y. So this is like the standard I/O trick where instead of checking against K, I'm going to check against a hard-coded value at this point. OK? And this falls from I/O security because these are two functionally equivalent ways of doing this computation. If I use FK or if I use K star with Y, it's the exact same thing. So this is I/O friendly. The next thing I'm going to do is use the fact that K is nowhere in this picture and replace Y with a random value. And this is the classic I/O trick with punctured PRS. So the point is because the punctured key says that K star doesn't tell me anything about Y, I can randomize it. Okay, so now we're at this point. I'm going to do this very clever trick by this work of GSWW, which says, okay, now I'm actually going to change this to, instead of checking pi equal r, I'm going to change it to g of pi equal g of r, where g is an injective PRG. So functionally, this is equivalent, right? Because g is an injective function. So whether I check pi equal r or g of pi equal g of r, it doesn't matter. So using the fact that this is functionally equivalent, I can make this change. Okay, and then finally, I can say, okay, at this point, r isn't really in the clear. I can replace g of r with a completely random value by the PRG security. But at this point, the cool thing is I can say that I can change this program to just actually always abort. Because with high probability, because I sampled u randomly, it's not in the image of this PRG. I should have said g is a length doubling PRG. So most strings are not in this image, so I can just do this randomization and get rid of the proof. So this is how you do it for one proof. Okay, I went a bit fast, but this is like standard I/O gymnastics. It's very unintuitive, but yeah, this is how you do it. And ta-da! Yeah.
Just a quick question.
Yeah.
Why did you use PRG to begin with? Does that affect your security parameter length?
Why did I use PRG?
Like,
because I want to do this step where I can say there's no proofs.
No, that's true.
Yeah.
I'm saying that you could just always check g of pi equals g of f, right?
Yeah, I could have said my first construction with that line,
Yeah.
but it doesn't make a difference. But it's the same thing.
Yeah, that's what. Yeah.
But okay, so we can do the same thing to remove all the proofs. I removed one proof, but you can sort of like try to do the same thing, go one step at a time, and incrementally remove all the proofs. Remove all the proofs. But the issue here, you can just remove all the proofs, but the issue here is that I'm actually using PRG security too many times. Because every time I remove a proof, I'm using injective PRG security, and that's 2 to the 2xi invocations of it, and that's bad because if you look at my verification algorithm, if my g is 2 to the x secure, then the pre-image needs to be like roughly size x, so pi needs to be size x, and I have not gained anything. I'm back to square one where my proof size grows with the configuration. And I do not want this. So the fix here, I wish I could talk more about this, but I would just say the very high level trick. This is a beautiful idea from Waters-Wu, which says that instead of using PRG each time I remove this proof, I'm going to do it in one shot by first planting a re-randomized PRG at every point, and then using PRG once. So roughly speaking, this is what it's going to look like. Instead of immediately removing the proof, I'm going to put check if g of pi is equal to like a re-randomization of the same PRG. So I'm not using PRG security. I'm using the fact that the PRG re-randomization is perfect. So now by using the same perfectly re-randomizable PRG everywhere, I can like plant the same PRG challenge. So if you give me any proof here, I'm breaking one PRG challenge. So essentially, I'm only using PRG security once per level, and this keeps the proof small. So this is like the key idea from the Waters-Wu paper. But I'm like really hiding a lot of details, but that's the high level. And zooming out again, so what's happening is from H2 to H3, for example, I'm using like exponentially many hybrids with I/O, punctured key, re-randomization, and so on. And then I'm only using PRG each time in each level. So the PRG security only needs to grow with T, which is OK, because we want log T size proofs. And OK, so I'll just very quickly say again how we use the trapdoor. We use the trapdoor first in the real world to decide what the adversary's cheating probability was. Then we used it in the ideal world to plant where I want to remove the proofs. And we used it to inductively remove proofs. And I really think this is the main thing that I cannot get rid of. For those of you familiar with Waters and Wu, I think they actually do take care of these two problems. It's this step that I do not know how to get rid of. And this is the open problem that I want to present. So open problem is get rid of this. OK, so to say again, this is IVC for trapdoor NP. Hopefully I've convinced you there's some interesting applications of this. And the trapdoor only appears in the proof, and we get succinctness that we want. And it makes sense, because again, I don't need anything about the intermediate configuration in this case to decide the language. So why would the proof size have to grow with the intermediate configurations? So yeah, we get polylambda size proofs.
I want to make sure I understand the statement. If you just put the trapdoor in the clear as part of your proof, I know it wouldn't achieve your application,
Yes, it will not.
wouldn't hide anything, but would it achieve the definition of IVC for languages with trapdoor computation trivially? I'll just reveal that.
It's IVC for P. It becomes a P time. Yeah.
Okay, well.
Actually, it's not P because you can still make many possible
I'll call it
jumps.
for languages in NP that have a trapdoor. Maybe that's the same as P.
Yes.
So, like, all the work you're doing is not just for IVC. You want IVC with, you want to use the trapdoor only in the proof. You want to give privacy. You want to not reveal the trapdoor. Like, there's some extra.
Yeah. So I'm saying
goals.
the fact that the trapdoor doesn't appear in the construction, it gives us very interesting applications. Yeah. So that's like. And
no, I'm not doubting the interest. I just want to see that I understood.
Yeah.
It's
like hiding IVC.
Yeah.
Something like that.
Yeah.
I only know an N-to-10 algorithm, but I know they exist, or assuming they exist, an order of an algorithm.
Yes.
Yeah.
As long,
what? I can't hear right.
If you think there exists an algorithm, you already get security, and you don't need to know. You don't have to have it in your hand.
It's anti-fungible.
Yeah. I agree. It's much better, but somehow it's like maybe you should define.
Maybe I should define it with more keys.
If you just achieve IVC, then it seems to be, here's IVC, I just published the trapdoor.
I see.
You're like...
Yeah.
I see.
Well, IVC
without revealing anything?
Yeah, oblivious to the
without
trapdoor,
revealing, without even knowing it.
Yes. So, maybe this should be inside this box, is what you're saying. Yeah.
Yeah, it's like an existential thing.
The summary, to extract or not to extract. We showed two IVC constructions in a non-deterministic setting. So the first one is very extraction-based, using classic rate 1 bar type techniques. And we get proof size, lambda, CF, and log t. If you don't want to use I/O, then you can also get something here. And then we give an I/O-based approach for trapdoor NP with no extraction. And proof size, polylambda, or polylambda, comma log t.
Again, sorry, I just
Yeah?
want to make sure
Yeah.
I understand the statement. Your second thing, the I/O-based approach, I could apply your construction to any language in NP.
Yes.
Just that it might be no good.
It might be no good.
And I don't know how to check it.
If I had to conjecture, I want it to be secure for everything. It might be, right? Because the construction doesn't use anything about this. And again, BBB says it's secure.
Prove it in this case.
Yeah. Yeah. So basically, the way we did this is we were like, okay, water smooth exists. Can we use these techniques for IVC? And this is where we really got stuck. But there was still something that's like a meaningful interpretation here. Plus, I really want to say this is a talk posing an open problem. Okay, so open problems. So I said this very briefly, but can we construct IVC in the ROM? This would be awesome, or impossibility results would also be great. And yeah, this is the open problem, IVC for NP with polylambda size proofs. Do you really need this extraction or this inductive step or so on? And another thing I didn't really talk about too much, but maybe this I/O-based technique could apply to PCD because you don't have to take this like half loss each time you extract. There's no extraction, so maybe this gives a pathway towards like other types of incremental computation. Okay, thank you. Sorry. Sorry, I only put one dog there, so I felt bad. Any questions?
Any other questions?
Yeah.
So, if we get back to the discussion about where does the size of the configuration enters in the prior construction. So, if I understand correctly, is because of this using of indistinguishability between statements, it only you can only say that an adversary cannot break it if it's easy to, or this is why it works for P, right?
Because because you could actually, it's a testable property somehow.
Yeah, exactly.
Yeah.
Do you think that for these trapdoor NP languages, we could somehow leverage the trapdoor to use it in the other construction?
I think so.
Similar about without no without IO, but
so
barred.
It's not that easy, right? Because when you're using the trapdoor, you have the configurations at hand inside the IO, right? But if you don't have access to the configurations, how do you even use the trapdoor, right? So in the first construction, the configurations were embedded in the proof.
Another thing I want to say that I guess I didn't fully say here is, actually trapdoors like explicitly avoid, let's say, the Gentry-Wichs barrier, and we didn't know how to use it before. So hopefully, there's a different kind of interpretation to this result. How do you use the fact that trapdoor languages, even if it's an NP computation, avoid the Gentry-Wichs barrier? So how do you leverage this fact? So this is one example, and hopefully in that direction, maybe you can start getting snarks for these types of languages from standard assumptions. So that's just a different takeaway I just wanted to say. My head got lost in there.
And one more question. You mentioned somewhere in the middle that you actually need lambda to be as big as this configuration. Can you say again why?
Yeah. So let me just find the slide. It's this one, right? So the problem is that to make this index hiding property and CRS binding property to actually go through, I need to be able to say, well, when I switch where the CRS is binding, the adversary doesn't change where he's cheating. But changing where he's cheating is not an efficiently testable property. You could non-uniformly decide it in time 2 to the configuration size, right? Like you can think of this, sorry, not uniformly, but you can decide it with a circuit of that size that just hard codes the truth table. But so for that reduction to go through, I need like 2 to the x security. So that means for the barg that I'm using, I need 2 to the x security. So that's where the lambda in the barg needs to be at least x.
In the CRS security, you mean?
In the CRS, yeah. The barg CRS.
For the
yeah.
index binding. So this is also for the index binding.
Yes.
Okay. So all of your length problems in this construction come from the reduction to index binding.
Yes. You need. It feels like you need some information about the path. And I will say that IO-based construction also works if you add this is like implicit. I think if you stare at this adaptively sound barg work, but where is it? Okay, this construction is also secure if along with pi I you add a hash of all the configurations so far. I'm just saying this as like an extra point. So if you give some help, this construction is secure for all of NP. Does this make sense?
And why can't you?
Because I don't want to grow with the configurations. I need the SSB to be binding on the intermediate configurations for the security proof to go through. So now I have to carry around this SSB. So we were just trying to get around the fact that I have to carry around this SSB. How can you do it?
The hash will be part of the proof, right?
Yeah, hash will not be part of the proof. So if you had this, you can think of like an updatable hash, this would actually work for all of NP. But it would not be better than our first construction, like the efficiency of the first construction.
Maybe we'll take other questions offline, take a 20-minute break.